And what else? 3 minus x if x is greater than or equal to negative 1. So again, you've got two graphs that you're going to deal with. You've got the graph of y equals 2x plus 3 and the graph of y equals 3 minus x. Individually, these are both linear functions. In fact, you can double check it by graphing these on your graphing calculator. We just need to kind of make some restrictions on these things because we don't want the complete graph. For instance, here, I want this for values of x less than negative 1. So let's come up with a couple values that we can choose. Now choose the endpoint. You want to graph the endpoint. In either case, it's either going to get a solid dot or a hollow dot, but graph the endpoint. If x is negative 1, what does y equal? 1. What's another point that satisfies x is less than negative 1? Be kind. Don't give me negative square root of 2 or something like that. What's a friendly point? Negative 2. Sure. I mean, you don't have to really go all, out on a limb to find this thing. It's just negative 2. If I put in negative 2, I get negative 1. Great. 2 points determine a line. I'm in good shape. How about over here? Let's do the same thing for this one. So x and y. Keegan, maybe you can choose a couple points for me here.
Negative 1 and 0.
Sure, negative 1 and 0. Perfect. Choose that endpoint, and then one other one that satisfies the domain requirements. So at negative 1, I'll get 4, and at 0, I'll get 3. Perfect. So let's graph both parts of those. In fact, tell you what, let's do it this way. I'll graph this one in green and this one in orange, just so that we can kind of, well, that's not showing up too good for you there, is it? How about blue? Is blue going to show up any better for us? No. Mix them together, blue and orange? Mildly better. Anyways, let's graph this, see what it looks like. So 1, 2, 3, 4. And I think I need a couple below here. One thing that helps you if you're stuck drawing your own graphs, it's really helpful if you draw your tick marks evenly spaced. Try and get them evenly spaced on each axis. So for the first one, I've got points at negative 1 and 1. That's up here. What kind of a dot am I going to draw at negative 1 and 1? Hollow or solid? Hollow. So negative 1, 1, hollow dot. Negative 2, negative 1. It's going to be down here. And then draw arrow, draw a line from there like that. So that's the first part of the graph. For the second part, I've got points at negative 1 and 4, and then 0 and 3. So negative 1 and 4 is going to get a solid dot. And 0 and 3 is just another point. Boy, that's not showing up at all, is it? Still not doing that good. I'll just use regular ink here. And there's the second part of your graph. there's a lot more piecewise functions around you than you may realize. Like postage stamps are a set of piecewise functions. The taxes you pay are piecewise functions. Even something in nature, like the speed of sound, is modeled by a piecewise function. So this one is solid, and this one's hollow. Yeah, and that corresponds to these points here. So the less than gives you the hollow, the greater than or equal to gave you the solid. Anything else on problem number 38? Let's reverse engineer one. It's going to be problem number 50 in your book. So I'll put that up here. It's on page 168. Stay. Good boy. Okay, so they've given you this part of it where they're telling you less than or equal to 1, between -1 and 2, greater than 2. But what we have to fill in is the actual functions. Now I'm thinking that a couple parts of these are going to be pretty straightforward. For instance, what's the function that I'm going to fill in to the left of -1? Yeah. Yeah, there you go. So to the left of -1, I'll have f of x equals 1. Yeah, that's terrible. F of x equals 1. Let's do the other easy part before we do the hard part. What's the other easy part going to be? For x greater than 2, what's the function? -2. So I've got those two pieces of it. And that's for x less than -2 and x greater than 2. I need this piece. So, oh, actually, should have been a -1 here. I need the equation of this line. So, well, I guess we can find it this way. Y equals mx plus b. That's stuff we're going to review later, but it doesn't hurt to look at it now. What's the y-intercept of this graph? 1. So that's going to be a 1. And now the slope, you can calculate because we get a nice visual graph here, or a nice visual display of this graph. The slope of a line is the rise over the run. So the rise in this case is a -4. 1, 2, 3, 4. Let's see, 1, 2, 3. -3, I should say. And the run is 3. So how does that simplify when I put in the rise over the run? -1. So that tells us our equation. It's y equals -1x, or basically -x plus 3. Or no, plus 1, sorry. -x plus 1. That's that remaining equation. So here's your piecewise function. F of x equals 1 for x less than -1. -x plus 1 between -1 and 2. And -2 to the right of 2. So I like that one. It's kind of reversing directions on this, but it's still a good one. Any follow-up on problem number 50? Let's stay in the book with problem number 52. Now this whole chapter is going to be loaded with information about functions, but one of the things you need to determine is whether or not something is a function. How can you tell based on the graph of something if it's a function or not? A vertical line test. Good. So if something passes or fails a vertical line test, then great. So how about this first one, Carol? Does that pass the vertical line test? 52. That passes the vertical line test? Vertical line would intersect that graph more than once, right? And if it intersects it more than once, it's not a function. How about part B? Does that one pass the vertical line test? Yes. Is there anything else that doesn't pass it? D. D fails it. So A and D fail the vertical line test. B and C pass it. So the only two functions graphed here are B and C. Let's move on down to the next even number problem, and that's problem number 50. Now we've dealt with domain a fair amount so far, but we haven't done a whole lot with the range. And this is a good problem because you can visually see both of them. First of all, is 54 a function? No. It's probably the graph of an ellipse. We'll deal with that later when we deal with conic sections. But the domain is the set of x values associated with a relation or function. So in this case, the set of x values would go between what and what? Good. So negative 3 to 3 would be your domain. Alternately, the y values, no, negative 3 to 3 is correct. The y values represent the range. What y values do I have for problem 54? Yeah, between 1 and negative 1. So let me write it for us here. For 54, the domain is negative 3 to 3. Or you could write it with interval notation. You could write it as negative 3 is less than or equal to x less than or equal to 3. The range is somewhat similar. Negative 1 to 1, or negative 1 is less than or equal to y is less than or equal to 1. The domain is always going to be your x coordinates. The range is going to be your y coordinates. Let's finish this up with, let's see. Let's do one more problem like that for domain and range. And that next problem is going to be 56. Okay, so again, you want to determine the domain and range. So try and look, what are the x values represented by this graph? What values of x have part of the graph associated with them? Where is the graph associated with the y values, or what y values are there? All right, so the x goes from, let's see, that'd be 0, negative 1, negative 2, negative 3. So negative 3 to where for the x values? Negative 3 goes all the way up to and including 2. So that'd be your domain there. The range is just the y values. And the range is going to require a little bit more thought here. you've got some y values here, but it's not the whole story. So what would we list for the range? Any brave souls this morning? Good. -2.
And then I guess if it was in notation, would you use the
And
not including 0 to 3?
perfect. So here's what we'll do. For problem 56, our domain was -3 to 2. And the range would be just that one number, -2, right? Was it -2 or?
Yeah.
I flipped the page. -2, and so that union 0 to, what did it go up to? 3? Now a little bit of comment here on the 0. I wrote a parenthesis around the 0. How come I wrote the parenthesis there? Yeah, we're not including the 0, right? Because x or y equals 0 is not part of the graph. But we can include things at 3 because there's a solid dot on the graph at 3. And let's take a look back at the graph. See that? So you're not including the 0 because 0 is not part of the graph in the y direction, but 3 is. So that's why we got that funny combination of parentheses and brackets on the range.
Why did you make 0 instead of 1?
For
Yes, it's on the y-axis, so you're starting from 0.
which part?
The range.
Well, the range is the y value. So I have a y value down here at -2, and then starting at the x-axis, which is y equals 0, the y values go all the way up to +3. Okay, good. Yes, sir. You mean with this little union here? It skips everything. So you got this one point. So I just put it as a set by itself. It's like, okay, you got that one point, and then you've got this interval. So I combine the two with, it's called a union. So it's this or this.
Would it be wrong if you just put the -2 in brackets, or?
Nah, if you wrote it like this, -2 union 0, 3. I mean, I'm not expecting you guys to be fluent in set theory or anything like that. I mean, I'd accept it. You won't see it in a book like that, but that's okay. I would accept that. Because what I want to see is that you understand that there's this point down here at -2. You're not including 0, but you are including 3.
If there was another one that was a line at -4, could you write it as a set -4, -2?
You'd have to use the braces here. Because if you wrote it like you were suggesting in parentheses, then it would look like an interval. So if you wrote it as, say, -4, 2, that looks like the whole interval, or -2. So the way you would write it if you had another line at, say, -4, it would be -4, -2, union 0, 3. Yeah, this says it's a set. You're just listing these rather than an interval, and you want everything between. So, but I probably wouldn't give you anything quite that messy. Yeah.
This is my last math class.
It's not. No, it's good. It's good to hear. It's good to hear. Okay, one last one, and I don't know. Do you want to practice more of it on your graphing calculator, or can I just show up here? So one last effect that we can do to our graphs of parabolas, and it's problem number 72. So if you want to do this on your graphing calculator, that's fine. We're going to go back to the graph of y equals x squared. But I want to play with this a little bit. And problem 72 asks you to put different coefficients in front of the x squared. For instance, y equals 1/2 x squared. So what's that 1/2 doing to my graph of x squared? Here's the graph of x squared. Here's the graph of 1/2 x squared. Yeah, it's making it wider. Okay, so let's try a different one. Instead of y equals 1/2 x squared, what if I did y equals, say, 2x squared? Yeah. So overall, what is that number in front of the x squared control? Yeah, how wide or how narrow it opens. You can really tailor your graphs of parabolas to match a lot of different phenomena. It's pretty cool. I think that's all I wanted for. What if I put in y equals -2x squared? Yeah. So you're going to have that same narrowness. It's just that that negative is going to flip things. So, yeah. So, again, some predictable effects that you can get when you're working with your graphs here. Anything else on section 2.2? For homework, try 9 through 19, 29 through 41, 49 through 55, 69, and 71. So let's see, that's 6 problems there, and then another 7 maybe here, 13, 4 more there, 17, 18, 19. So that's not too many problems. Hopefully you can get through that. You do have an exam on Tuesday. It's a question. Let's see, that homework starts on page 167.